Good morning, good afternoon, wherever you may be in your day. Thank you as always for choosing to make chemistry part of your day. Today we're going to do some math, which I like to think of as comfort food for chemists. So hopefully you're excited about this. We haven't done math in a lot of the other videos. So the way we do math in chemistry is dimensional analysis, where we're using the numbers and the units to help us go through a problem. So what would that look like? I find a lot of times the problem isn't with the math. It's breaking down a word problem. The longer the word problem, even if it's got less information, there tends to be a barrier with people. So let's take a typical, fairly succinct word problem and see if we can attack this. A bat's heartbeat will beat an average of 1 billion times over its lifetime. That's true of most mammals. It's also true that then from its heart rate, you can tell how long the life expectancy is. So if a bat's heart rate is 750 beats per minute, what would be the average lifetime in years? All right. A lot of times they show in the literature that if the problem's a real-world problem, you're more interested in doing it, more interested in the class, yada, yada, yada. A lot of times in the first sentence, there's really no usable information. Now, I didn't do that in this example, but a lot of times in the book, that first sentence tells you the background about why you'd want to do such a calculation. Once you determine there's nothing in there other than background historical information, cross it right out. Don't even worry about it. What I really want to focus on is what's the pieces of information in the problem. So, 1 billion beats. If you want to say times, or you want to think of this as beats, that's a good idea. We don't care that's a bat. We don't really care that's a heart. We don't really care that's an average, but we do care that we're going to use that number of beats over its lifetime. So if you want to think that beats per lifetime, that's fine as well. If a bat's heart rate is 750 beats per minute, that's certainly a number we want. What is the average lifetime? And this is always important. What are we asked to solve for? Because we're always going to work backwards on problems. So the average lifetime in years, and that's our question mark. That's what we're solving for. So those are the pieces of information. The rest of this we can pull out, and I really want you to do this with your word problems. Take the information given, pull it out, and list it. Don't worry about the word problem. Let's take the word problem right out of this. So what would it look like if we did such a thing? There's a couple ways of doing that, but let's take a look at this example. So I just said 1 billion beats. That was a given. It's a piece of information specific to the problem. It's not a ratio. It's not a known. It's not a conversion factor. It's a given in the problem. And I want you to think of these things because we're going to do what I call railroad tracks, where we have tops and bottoms for everything. So when it's a given, the other side is going to be a 1. It's not really a 1. It's just a mathematical placeholder. But I do want you to think of all these things as kind of pairs that we're going to use in the railroad tracks. And if it's a given, the other half of the pair is just a blank space, or mathematically, since we're multiplying and dividing, that's going to be a 1. So that's why I have the quotes around it. It's not a true 1 mathematically. That's not a true statement, obviously. But it's going to be for the way we set up the math. Okay, so we have 1 billion beats, 750 beats per minute. That means every minute there's 750 beats, or every 750 beats there's a minute. So this is kind of a true equality for the way the problem's set up. And I want you to think about it that way as well. And then we're looking for the lifespan in years. So I always use a question mark for what I'm looking for. You want to use X or smiley face or V for victory over math. Whatever you would like to use, that's fine as well. And then since we're looking for time in years, and the only time up here is minutes, we're going to need relationships between years and minutes. So I just went ahead and wrote those down. You probably all know there's 60 minutes in an hour, 24 hours in a day, and 365 days in a year. If you want to be more precise and say 365 and a quarter, that'd be fine as well. Okay, so how do I solve this problem? And you can see I left myself some space, equal sign. Always start backwards. What am I looking for? So I'm looking for the number of years. That's a unit of time. Very good. And there's two ways to approach this problem. I'm going to do the way where we literally just look at the units and view this as a puzzle piece. And we don't really think about what we're doing other than just logic and puzzling. So, of our pieces of information up here, what's our only other unit of time? Our only other unit of time is 1 minute. So if we have time is what we're looking for and it's on top, we're going to put our time here and we're going to also put that on top. These boards are a little big. So I'm going to put my 1 minute up here and my 750 beats down here as my ratio. So that's the whole idea of the equals. One goes on top, one goes on bottom. We always have something on top, always have something that goes on bottom. Now, if we're looking, we can do this two ways. We can either take care of the bottom or the top. Let's do the top. Let's continue with this puzzle. We have time on top, time at the end. That's a simple unit conversion. So do we know how many minutes in a year? No, but do we know something that can bridge between minutes and years? Sure. We know that there are 60 minutes in an hour, 24 hours in a day, and 365 days in a year. And what I suggest you do is when you're doing this, actually make sure that the tops and the bottoms cancel out. Anything divided by itself is 1. So day divided by day is 1. 7 divided by 7 is 1. So those go away. And if we look at what we're left with right now, and I'm not concerned about the numbers, just look at the units. Across the top, we have years. Across the bottom, we have beats. So we have years per beat, which is getting us close. We have to get rid of the beats. So is there another piece of information we haven't used yet? Sure. Does it have beats? Sure. Beats is on the bottom, so to cancel it out, we want beats on top. And then we'll put our placeholder down here. Now, if we look, we've solved the problem. All we have to do now is punch it through our calculator. So you're just going to multiply all the numbers on the top, divide all the numbers on the bottom. So this might look like, in your calculator, 1 times 10 to the 9th, divided by 750, divided by 60, divided by 24, divided by 365. If you do that, you'll get for an answer 2.5 years as the average lifespan for a bat, which is about right biologically. Okay, let's go back a second. You don't need to use all the parentheses on your calculator, you certainly can. I hope you're using the scientific notation button on your calculator, in which case this should probably look 1E9. Your calculator takes that E and makes it times 10 to the whatever. So this would be 1 times 10 to the 9th. If you're using Excel, it would look the same if you're doing that mathematically on a computer. So just to let you know, just multiply across all the tops, divide all the bottoms. I wouldn't do multiply, divide, multiply, divide, multiply, divide. It's kind of easy to make an order of operation error. And if you do it this way, you don't need parentheses. The other way is you'd have to put parentheses around the whole thing. But I like to just multiply the tops and divide the bottoms. Least number of button hits on my calculator. It's kind of a clean way to think about going about it. Doesn't really matter. Make sure you get 2.5 years. All right. I promised you 2 approaches to this problem. The other is, a lot of times to solve a problem, what you really need to look at is what's specific to this particular problem. Lifetime, that's generic. These are generic. So what's more specific to the problem at hand? That a bat has exactly 1 billion beats, or that you had a rate of 750 beats per minute? I would argue that the most specific piece of information up there is the beats. So I might start my problem with that. And use that mathematical placeholder. And then we do the same process, right? We'd say, okay, I gotta get rid of beats. The only thing I have in here with beats is this. So put beats here, put minutes here, and then you go about the same thing. Do I know a relationship between minutes and years? No, but I do know minutes and hours. I do know hours and days, and I do know days and years. And notice what I just did here, because I do this a lot. I'll put in all the units and not worry about the numbers. Because if I can put the units in and get them to cross themselves out, so this is what I mean by a logic puzzle. If I can get those to cross out, I know I solved the problem correctly. Years is left on top, nothing's left on bottom, or 1 mathematically. And now I know I can just put in the numbers. So how many hours in a minute, or vice versa? 60 in 1, 24 hours in a day, 365 days in a year, and I can put the numbers in, and I'll get the exact same answer. So that's another approach. What's it look like if I pick the wrong thing? Because sometimes people are just, I don't know where to start, which is, never say that to me. You can always start. I know getting stuck in the middle is very easy. Making mistakes is easy. I do it myself, trust me. But where do I start? Start with what's most like your answer, and then try to make it work. What's it look like if you put the wrong thing on top? Well, you can, it's not that bad, really. Let's say you put 750 beats over minutes. That's a common thing people might start with. Always remember where you're going, and you'll know if you're wrong. 750 beats per minute. And then I know I want years, so I'm doing the same thing. 60 minutes in an hour, 24 hours in a day, 365 days in a year. And you're like, oh no, it's not where I want it. And there's a tendency to just scribble this out, erase it, cross it out, throw out the piece of paper, and not use this. But you're really close to being right. You've used all this information. You've canceled it all out properly. You've gotten down to years. And you can use your beats. We'll use our 10 to the 9th beats. And we've almost answered the problem, which is everything flipped. So you can do two things. You can take your answer, and you can do 1 over your answer, and that'll flip it. So if you're 1 over years, 1 over years will give you years. So if you do end up with the wrong thing on the bottom, or your units are flipped from where you want them, go 1 over. There's actually a -1 button on your calculator, a function. Let's see how it's written on mine. Mine looks like this. There's a button in my calculator like this. That's an inverse button. That'll do the same thing mathematically and flip it for you. So you can do that, or you can just go back to the beginning and just literally, if you worry about your math skills, just go back and flip everything. And you get that. So you get that same answer. So there's ways to approach this. So don't just scribble it out. If you're putting things together and they're canceling out and you're close, but you're flipped, same thing with your solving for problems. 1 over x, just make sure that's different than x. Okay. One more quick example using powers. What's a better deal? An apartment that's 975 square feet or 225 square meters? You might guess this is a trap question. It must be the smaller number. You might be right. But let's take an approach. We can't compare apples and oranges without at least an apple-orange conversion factor, which I do not have. So we can't do square feet to square meters and pick the bigger or the smaller number per se. We need to make them both the same thing. And in this case, I'm going to choose to make square meters into square feet. Doesn't matter, you could do it the other way, but since we typically do square feet in America for our advertisements, I figured let's convert it to the American unit. Okay. So, if you notice, 2 squared is what? 4. Awesome. What's 2 cubed? 8. Good. How do you do that? You did 2 times 2 times 2. So meters squared is meters times meters, and meters cubed would be meters times meters times meters. So I've broken this up here just to emphasize it, but this is, just realize, this is the same thing as meters squared. What this means is we got to convert this twice. So, this is a unit of length, this is a unit of length, it's just a conversion factor. Now it's metric to English, and I promise you, I will always in the problem give you 1 English to metric conversion factor if necessary. You don't need to memorize these. Now, I might not give you the one you want, but I'll give you one. So, for example, 1 inch is 2.54 centimeters. So we have meters. You might guess I need to get to that centimeters that Dr. Virgo gave me, and that's true. So I could put meters here, centimeters here, and I know that relationship, 100 years in a century, 100 centimeters in a meter, and that's true. Now my question is, does that cancel out meters squared? And I would argue no. Partially does, right? We left meter, centimeter, which isn't really a good unit. What we need to do is we need to do that twice. So you literally could write on your piece of paper, you could write this down twice and cancel out that way. And that's a good way to make sure you don't make stupid, silly errors. But a little bit more sophisticated way of doing this is square it. Now, what I would like to point out is if you square this number, everything becomes squared. 100 squared, centimeter squared, 1 squared, meter squared. So when you're going through your calculator, don't forget they have to square everything. Now that'll cancel out. So now we have centimeters, so we can use our conversion factor, 2.54 centimeters in an inch. And this again becomes squared, squared, squared. And I'm just going to distribute it through just to emphasize how that gets squared. Now we can go inches to feet. And 12 inches in a foot, and again, square, square, square. If we go through, do a little mathematics, 2,420 square feet, and you are right, this is a trap question, and the smaller number is actually the bigger number, if you will. So, the better deal is the square meters. Always good to go back and see, did I answer the question? It's great that I got an answer, but did I answer the question? I hope you find this helpful. We're going to do more of these types of calculations throughout the entire semester. Thank you for your time, and have a wonderful day.